Hello, my name is Gustavo Almeida, and I'm one of the CFD engineers here at ENGYS. Today, you're very welcome to join me in this webinar of the Learn by Example series, in which I'm going to talk a little bit about vehicle aero-thermal simulations in a coupling process using elements. So, starting with some webinar's goals, today I'm bringing to you a few words regarding vehicle thermal simulations in order to introduce some relevant considerations related to this kind of application. By the end of this webinar, expect to expand your understanding on how elements makes your automotive cases workflow smoother, even if your workflow requires coupling it to a different software. And for this particular case, I'm talking about TAITherm. Finally, I'll be setting up a coupling workflow between elements and TAITherm, and I intend to accomplish all of those within 20 minutes. We would love to hear your questions, and they will be answered by email afterwards. Right, so in our previous webinars, you have seen some important considerations related to external aerodynamics, vehicle tire modeling, and porous media simulations, and how we can easily set up and obtain good results for that using Elements framework. All of those combined to certain modeling strategies such as vehicle operation point, whether it's at constant speed or at a soak phase, meshing, thermal libraries, and so on, are key points to what I'm presenting here today and correlate directly to thermal simulations. The flow passing through the vehicle front grills and around its wheels, cooling engine bay compartment, and brake system components is called internal flow, and this internal flow is what directly affects the vehicle cooling performance. Okay, now what's the role of thermal analysis in vehicle design? The core aspects of performing thermal analysis are improving engine performance and identifying potential hotspots in the process which could affect the safe operation of the vehicle. That leads to evaluation and design of thermal shields and heat sinks along the process. Obviously, there are many other relevant points in such analysis, such as having a thermal management assessment, human comfort evaluation, structural thermal damage analysis, and so on. That said, there are some fundamental considerations which should be made in order to obtain more accurate results at the end of our simulations. As we're talking about internal flow, the full car geometry is usually considered, and so our CFD model shall account for good mesh quality and resolution within the engine bay compartment, so that all the relevant features for correct flow field and heat transfer coefficients computations is achieved, such as small gaps capturing, finer mesh resolution and pressure drop curves for radiator cell zones, and so on. At the same time, we try to keep our final mesh in such a way it does not become computationally expensive to solve in a reasonable time. Additionally, our thermal model shall accommodate the most level of fidelity as possible, modeling things like coolant fluids, using thermal libraries for some components like, for instance, the air intake system, and using exhaust streams to better represent the vehicle exhaust system will bring the most out of our thermal simulations and will contribute to accurate results in the end. So, regarding using elements within a 1D, 3D simulation coupling workflow, the case I bring today couples elements with TAITherm through an interactive process. TAITherm is responsible for performing 1D conduction and radiation calculations using the desired thermal libraries, generating temperature boundary conditions as output to be used within elements for the surfaces of interest. In our case, the entire vehicle geometry is mapped to those temperature calculations. Elements is able to read those files and then run the entire CFD model to compute the resulting flow field to map the convective heat transfer coefficient and surrounding fluid temperature back into the thermal model. There are many ways to create our workflow, and as you can see here, we adopted a ready-to-use template already distributed with GoTherm. If you go through each of these boxes, you see each individual process for both the thermal model as shown here and the CFD model as shown here. You see that each one of those boxes perform one or multiple tasks at the end. The model checks the defined convergence and stopping criteria. And so the process goes automatically. We can either run this coupling process in a local workstation or in a cluster. Alright, so now it's time for the learn by example part. For today's example, I'm starting the process with the thermal model fully set up and with the basic procedure already performed in Elements Aero-Wizard for setting up a case, as per one of our previous webinars. The case in question is the simulation of a SUV-like dry air vehicle geometry. For this particular case, I ran a steady-state CFD plus a steady-state thermal model, but it's worth mentioning that pseudo-transient and fully transient models are also possible to run. Well, for thermal analysis, some adjustments in element setup shall be made in terms of solver selection and boundary conditions, or for more advanced users, a customized template may be used in order to perform such kind of setup within Elements Aero-Wizard. The standard meshing algorithm is used, and the domain is comprised of hex-dominant cells. The simulation state is then set to steady with incompressible flow model and k-omega-SST for turbulence modeling. The vehicle is assumed to be at a constant speed of 140 km per hour. For the radiators, a porous media cell zone is created and fixed temperature source is applied, representing the temperature of the radiator at that operation point. The heat exchanger fan is modeled using the MRF approach. The wind tunnel boundaries are assigned with fixed value boundary conditions with ambient air temperature, as the vehicle surfaces are assigned with the same temperature just as the initial gases, once the coupling workflow automatically maps the temperature of each individual component along the process from the thermal model. Okay, so now let's see how our coupling process is set up so that everything is properly addressed. Let's start with TAITherm. If we go to TAITherm, there we can define all the conditions for our thermal model to run, and I'm not gonna dive into much detail here. So if you want more details about the software, how it works, and how you can properly define things in here, you can go and check with our colleagues in thermoanalytics. As I mentioned, we're starting here from a thermal model already set up, and I'm gonna just point out a few things in order to have an overview of what's important for this kind of coupling process. So here under Editor tab, we see that there's the part selector in which we have this drop-down list. We can select each individual part of the thermal model, and then we can assign the proper conditions for it, like for example material, sources. You define the initialization type, but the most important thing here for us is that we are importing both the heat transfer coefficient and the fluid temperature. Now if we go to the Analyze tab, we can define here the maximum number of iterations we want the solver to run, as well as the end time for transient simulations. It's worth mentioning that for this particular case, as we are defining a steady state simulation for both the thermal model and the CFD model, we need to specify here the end time as 0 for TAITherm. Now let's go to Elements. Here in Elements, we are starting from a case already defined using the external Aero-Wizard, applying the open road defaults for the current model. So there are just a few things we need to adjust in order to have the model properly running. So under the Setup tab, we go to Solution and change the time from transient to steady, enable energy, and under modeling, we enable buoyancy. Now the most important thing is the thermal boundary conditions. Under the external boundaries here, we select one or multiple surfaces of our vehicle. We go under Thermal, Edit Selected Patches, and here we use the type boundary condition as mapped from file, which will grab the values of temperature for the vehicle surfaces. Here we specify the field, we want the temperature. Here we assigned the temperature just as an initial guess, as I mentioned, for the parts, and here I'm using the ambient air temperature. And then we point out the file that will be written by TAITherm. This is the basic process. After we did this, as I mentioned, we are using the ready-to-use template in CodeTherm, and this template particularly requires us to initialize the solution and then reconstruct the case so that it becomes serial. And that's because CodeTherm decomposes the case along the decoupling loops, and this is done automatically. So I'll not be hitting the button here just because this case is already set up and our coupling process is already set up. So now let's go to CodeTherm. This is CodeTherm's environment, and as I mentioned, our logical process is comprised of these assembled blocks, and if we go within each individual block, we can see that there are many steps followed within each block, which basically is telling to run the solver and export the results. So now let's focus on run CFD block. If we check this block, we see that the case is decomposed, the temperature boundary conditions are updated according to the resulting temperature surfaces written into a file by TAITherm. We update the control dictor with the writing frequency. We run the solver, and finally we export the CFD results. And so the process goes. Here we have the key properties tab, which need to have some few things properly addressed in order to have the coupling process running correctly. For example, we need to have the paths to the executables, the number of processors. We want to run both the thermal and the CFD model, the paths to the models themselves, and these filter rules, which basically tells to each individual model which surface we need to map and write to the resulting files. The maximum number of coupling loops and the stopping criteria as the target surface temperature change, writing frequency, and so on. And so the coupling process goes. Now, since we get everything defined in here, we simply press the start process button. After our coupling process has finished, we can go back to Elements and check the results. So we can, for example, go to the View tab, create our scenes, and do lots of post-processing for like I'm doing here on checking the surface temperature, creating isosurfaces, checking the velocity field around the vehicle and within the engine bay compartment, as well as the temperature field. It's worth mentioning that for cases like this, sometimes we want to have defined some scenes and use those scenes with our runtime post-processing feature so that we can generate the images as the process goes. That will make our post-processing procedure much easier along the process. Finally, a few home messages for you to take after this webinar are that vehicle thermal analysis are complex and provides us means for improved and safer vehicle design. A smooth setup for vehicle thermal analysis in a coupled framework is achieved with elements. Modeling strategies and best practices are key points for obtaining accurate results, and Elements provides highly customizable ways for doing so. Keep posted with the past and upcoming webinars of this Learn by Example series in our YouTube channel, as well as a lot of interesting CFD related posts in our blog. Thank you for watching.